Now, also there are different types of problems, right. So, we are also will like to do some exact differential problems. So, say f x y is a function of x and y, and d f is an exact differential only if we know the formula, right, only if this condition satisfies. Based on the above definition, which of the following would be exact differential? So, if you remember, the formula for exact differential was that I can write f as del f del x at a constant y dx plus del f del y at a constant x dy, which we are calling as m dx plus n dy. So, since the first m is the first derivative of x, the condition of exact differential is I have to now do with the derivative with respect to y, because we have already done with respect to x when calculating m. Now, we have to do with respect to y at a constant value of x has to be equal to. So, n is a derivative with respect to y already. So, you have to do now with respect to x. If this condition is satisfies, then it will be an exact differential. Now, we have to identify what is m and what is n. As you can see, m is 6 in the first problem, m is 6 x to the power 5 and n is 1. So, let us calculate for the first problem. Let us say I call it 1, 2 and 3. Let us say for first problem 1, m is 6 x to the power 5 and n equal to 1. So, del m by del y as at a function of x is 0, correct. There is no y dependence, and del n by del x at a constant y is also 0, because we are just doing for the this thing. So, first one is an exact differential. Okay. Now, I have to erase it. Now, let us do the second one. For the second one, m is cos x and n is minus sin y, okay, that you do not forget, because we are always talking about pluses now. So, it is minus sin y. So, as I said, m is already a derivative with respect to x, that is why it is. And how do you know that whether it is derivative with respect to x or not, because you can see there is a dx here, which means this must be already a derivative of x. Now, we have to do with respect to y. So, del m by del y at a constant value of x is equal to 0, del n by del x at a constant y is also 0. So, did you understand this particular part, that why I am identifying cos x as already a derivative with respect to x? Because I have to do df by dx at a constant y, then dx. So, because there is a dx here, which means this is already a derivative with respect to x. Now, I have to take a derivative with respect to y. M and n does not matter. What matters is that what was the first derivative. So, you see that this is also an exact differential. Now, comes the third one. Hopefully, it will be not, because otherwise we will not learn what is this thing. So, again x is already a derivative with respect to x. So, now I have to do with respect to y, which is of course going to be 0, and then right hand side I have to do with respect to x, and which is going to be 0 also. Okay, let us change that now. Let us change that. Let us do a different one. Okay. Let us give you another df, which is I am just changing, instead of x dx and sin y dy, I am taking the 3 and reversing it, sin y dx plus x dy. I have just reversed it. Okay. So, now I have to do with respect to, in order to calculate that, since already I have a dx here, which means first derivative was already with respect to x, which is sin y. Now, I have to do with respect to y. So, d del del y of sin y at a constant value of x is equal to cos y, right, and del del x of x at a constant value of y equal to 1, and now they are not equal, right. Cos y is not equal to 1, and therefore, this df is not an exact differential. So, this is an inexact differential. Okay. So, if I interchange this, another one, that also will be the same thing. So, for example, if I take the second one and interchanges df equal to minus sin y dx plus cos x dy. So, I have to take a derivative with respect to y for the minus sin y. So, del y of minus sin y is minus cos y and del at a constant x, and del x of cos x at a constant y is minus sin x, and they are not equal. So, therefore, they are also, this is also not an exact differential, it is an inexact differential. Okay. Okay, good. So, now comes another problem. Obtain a relation between del h by del u at a constant p and del u by del v at a constant p. We have to see that both are kind of at a constant pressure, right, and we also know the relation between h and u. So, h is u plus p v, right. So, d h will be what? d u plus p d v plus v d p. Every term will be there, because we did not put any condition yet, as of yet. Now, we are going to take the derivative with respect to u, del h by del u at a constant p. So, it will be del u by del u going to be 1, right, plus p del v by del u at a constant p, okay, plus del v by del u at a constant p, but dp is 0. So, this term will be 0. Now, you see it becomes very simple, is that del h by del u p, I have got del u by del v, we got del v by del u though that, but we can manage that. So, which means that I can write that 1 plus p by del u by del v p, it is in a reciprocal relation, right. So, what I am saying that del v by del u p is 1 by del u by del v p. We will see that, like we can write that as a reciprocal relation. Okay. So, another one, that write expressions for dv and dp given that v is a function of p and t. So, v is a function of p and t and p is a function of v and t. Okay. So, dv and dp given that, so that is very simple, right, because v is a function of p and t means we can write dv as del v by del p t dp plus del v by del t p dt, and similarly we can write p also the same way, dp equal to del p by del v t dv del p by del t v dt. We can write these two. Now, deduce the expression for d ln v. Now, so problem A is done. This is how to express dv and dp, basically how to write the total differential. Now, problem B is deduce expression for d ln v. So, d ln v is what? What is d ln v? 1 by v dv, that is the d ln v, right, and we already know dv. So, you can just write d ln v just by dividing dv by 1 by v. So, it will be this term divided by 1 by v and d ln p in terms of the coefficient of thermal expansion. This is isothermal compressibility and this is coefficient of thermal expansion, which tells you that given a temperature how much change of the volume will be there, an unit change of the volume. So, you can see that this alpha equal to 1 by v, alpha is the coefficient of thermal expansion. So, let us say if the temperature changes by 1 degree at a constant pressure, how much the volume will change and normalized by the volume. So, that gives you an idea that what is how much expansion is possible for a liquid or gas or whatever. Something will expand more, something will expand less depending on the alpha, and this is called isothermal compressibility. Why isothermal? So, because the temperature is fixed and say how much the gas can be compressed, and that is why there is a negative sign, because negative sign indicates compression. how much the volume change will be there if you pressure the system. Okay. So, these are the quantities also called heat capacities apart from Cp and Cv. So, and these are all measurable quantities. You will see in future that for any kind of partial derivatives, people should express in terms of these quantities. So that we can calculate them experimentally. Actually, we can measure them experimentally, rather we can calculate the value using the experimentally measurable quantities, which is this alpha and kappa t. Now, you can see, so 1 by V dV, which means it is del V by del P. So, what okay. So, 1 by V del V by del P T dP. So, I am writing dln V plus 1 by V del V by del T P dt. Now, what is 1 by V del V by del P? 1 by V del V by del P at a T is minus kappa T. So, it is minus kappa T dP, and what is 1 by V dV dt? This is alpha T. So, alpha dt. Okay. So, we have expressed dln V in terms of this measurable quantities kappa T and alpha. So, given this kappa T and alpha, if there is a change in temperature, we will know how much change in dln V will be there. Similarly, dln P also one can write as dln P as 1 by P del P del V T dV plus 1 by P del P del T V dt. Now, here you can see that it is instead of del P del V, it is del P del V del P, it is del P del V, it is just the opposite of that. So, del P del V will be from this equation minus 1 by kappa T. So, 1 by minus 1 by kappa T into P dV plus what is del P del T? Okay. So, del P del T is not there, as we cannot write that directly as this isothermal compressibilities. So, you have to wait for this quantity to be expressed in terms of compressibilities. When we will discuss about how to change these partial derivatives into different forms, that time we will discuss about what will be the measurable corresponding values of this one. Okay. But all of them will be possible to be converted in terms of these measurable quantities such as specific heats CPCV, alpha and kappa T's, and there are some adiabatic compressibilities which is called kappa S. So, the point is that whatever partial derivative will give, we should be able to get the value of those by or express them in terms of measurable quantities. Okay. Experimentally measurable quantities, and experimentally everything you cannot measure. You cannot measure the change in U, you can measure probably enthalpy, you can measure heat, you can measure pressure, you can measure volume, you can measure change in volume with respect to pressure, you can measure change in volume with respect to temperature, but you cannot measure change in enthalpy when you change an internal energy, you cannot measure that at a given entropy. For that we need to convert it to something that we can measure, and that is the whole thing that we will learn later on. Okay. And this is very simple, show that du by dT P equal to du by dt V for ideal gas. So, remember we will do that again, du equal to del u by del V T dV plus del u by del T V dt. Now, we have to do one more derivative, which is del u by del T P, which is del u by del V T del V by del T P plus del u by del T V, del T by del T is just 1. Now, we already know that del u by del V T is 0. So, this quantity becomes 0 and it gives us del u by del T V. So, for ideal gas, change in internal energy with respect to temperature does not matter whether you do it with at a constant pressure or constant volume, it does not matter. In fact, when it is at constant volume and temperature does not change, means pressure also does not change. Okay. So, we will stop here.